Greetings, everybody. Welcome to today's lesson. We shall be looking at centers of measure in geometry. Specifically, we'll be asking what is a centroid and what does it have to do in, or what is it in the context of a triangle or a square or a rectangle. Now, using GSP, which is the sketchpad, which we'll see in a little bit, we'll be able to investigate by creating to find what the centroid is in these figures. And then we'll give its relevance by explaining its importance in real-life examples. Other things to point towards are that this lesson can be introduced as young as really the 5th grade, middle grades there. I found that some of the Common Core mathematical standards that matched with this lesson are that in 5th grade, there's a standard that mentions how we ought to classify two-dimensional figures into categories based on their properties. And then in 6th grade, it followed right on, telling us that we ought to look into solving real-world mathematical problems involving area, surface area, and volume. Now, using GSP Sketchpad, we'll be able to investigate on how to go about to perform this very high complex mathematical functions. And then in general, the purpose of using this tool GSP for the Sketchpad is to introduce efficiency in the classroom activities by allowing dynamic interactions with the Sketchpad to explore, observe, build conjectures, and attempt proving. Following that, I found that this aligns, the use of technology aligns with Common Core mathematical practices in the sense that the Common Core standards they inspire us to initiate students to become researchers in an independent way. So the use of Sketchpad really helps students in applying procedural investigative methods to build these conjectures that then will help in understanding proofs and axioms that are constantly used in the world of geometry. Now, we will turn our focus to part of geometry that's called Euclidean geometry. So in Euclidean geometry, really, triangles are the simplest polygons. And triangles are interesting for many reasons because they are rigid polygons and they are frequently used in the construction of buildings and bridges. Triangles also have interesting properties related to their sides, angles, and areas and the centers. Now we will explore the triangle centers. So let me open a new sketchpad, and this is the one we'll use. Now let me remind you that in data analysis and statistics, the measures of center that are commonly used are arithmetic mean and median. In statistics, the median is the middle value of an ordered data set. But in geometry, medians are segments between the vertices of a triangle and the midpoints of the opposite side. They can be used to find a type of center for the triangle, also called the centroid, which occurs at the intersection of the medians. And physically, the centroid of a triangle is its center of gravity. So this means that if you cut out a triangle drawn on a uniformly dense piece of cardboard and you find its centroid, ideally you would be able to balance the triangle on the top of a sharp object by placing the object at the centroid. Now let's go ahead and make our sketch. Alright, so bring the cursor right here, and then let's do that. Okay, and then we're gonna have to go back on top of that to make our lines for sure. Grab the line, make your segments, and then after that, so we've got a triangle there. After that, let us name the vertices. So come back here and name your vertices A, B, and C. Next, we need to find the midpoint segment in these vertices. So bring the cursor back here, put it right there, construct midpoint on the segment. Ooh, that's not right. Construct midpoint. There we go. And then construct midpoint. Okay, right there. Construct midpoint. All right. And at this point, start working from the vertice to the projected midpoint of the segment that is right opposite from the vertice. So we shall bring back our cursor to the segment, to the construction of the segment, and then we'll extend it from a vertice to a midpoint, a vertice to the opposite midpoint, a vertice to the opposite midpoint. And then let's grab a point and place it right in the middle. And at this point, this will be called our centroid because it's the point where all our median projections have intersected. Okay. Now, from this sketch, there are a variety of different relationships that could be investigated. Relationship may be noticed by looking for things that don't change when objects in the sketch are changed by dragging. For example, one might notice that a point remains fixed and that two values maintain the same ratio, but we'll find this after we find the measurements of our side lengths there, and that two polygons appear congruent or similar to each other. Now, a conjecture is generally formulated that comes about from inductive reasoning or general statements being based on a variety of suggestive examples. Now let's go ahead and do some more work on our sketch. If we extend, put it right there, let's try to extend a vertice. Well, notice that as I extend that, two of the sides will extend together with it, but there's always a side that is consistent, just so we maintain the qualities and the characteristics of a triangle. And then if you try to move the centroid, really, you're moving the whole figure. And if you try to move the midpoint, actually, let's put up, I'm going to put up here some of the measurements so that you see how these change along. One of the most important things to notice is that as I extend or dilate the vertice, the ratios over here on the top right will stay consistent, and that can be investigated by just observing them in real time or pulling up the calculator and looking at how they change as I dilate and reduce that. Now with this, we shall move on to investigating a polygon in the form of a square. For the construction of the square, we need to go back to our definition. What does it mean to have a square? It means that we have four congruent sides with a 90 degrees angle in each corner. So I shall go ahead and construct that. Alright, now here I have my square, and a way to confirm that it's a square is that I put my measurements up here, and each side length is 6.28 and each angle is 90 degrees. Actually, I'm missing one side length, and JG, HG, IH, oh, I'm missing IJ. So let's find what IJ is. IJ, measure distance. Whoop, wonderful, 6.28 just as the rest. Now, we're looking for the centroid of this figure, so how are we going to do that? Well, without loss of generality, we know that in the triangles, we worked with finding midpoints of the three side lengths. So let's go ahead and divide this square into two triangles. Alright, I went ahead and found my midpoint of each segment of my square. After that, what I'm going to do is I'm going to connect from vertice to the opposite projection of a segment's midpoint. Okay, the way to do that is to grab the segment, go from the vertice to the midpoint, vertice to the midpoint, again, vertice to the midpoint. Same case here, vertice to midpoint. This is the other triangle, vertice to opposite midpoint, again, vertice to opposite midpoint. Now, I would like for us to observe, hopefully, that we have this rectangle right here in the bottom and the top rectangle. But the connecting dot is right there in the middle. And whereas these are the two midpoints, let me put the two midpoints of each rectangle. Whereas these are the two midpoints, the center point of the segment from right here to right there has already been found. So this shall be the centroid of our square. Now, without loss of generality, we can apply the same concepts while we're working on a rectangle. So I will go ahead and construct our rectangle and we shall work from that. The definition of a rectangle is that I have two pairs of parallel lines, and the vertices are connected by each side being a perpendicular of the other to make angles of 90 degrees. So I have a side length here, and in order to get its perpendicular, I shall click right there, click right there. My bad, actually, that is not correct. Let's get rid of that. After I have my segment, move the cursor back up here, click on this segment, click on the endpoint, and you would like to construct a perpendicular line in order to give us that 90-degree angle as they connect at the vertice. And then we would like to create another perpendicular to this line. So let's put a point somewhere on that line, really, to give us that side length, and bring the cursor back here. In order to get a perpendicular that goes across here, we'll click on these two, the side length and the point, and then we'll construct a perpendicular again. And we will need to do the same thing. We'll need to do the same thing in the bottom here. So bring the cursor back up here, click on the segment, click on the point, and then construct perpendicular line. After inputting the measurements of the side lengths together with the angles, I affirm that indeed I have a rectangle. I have two sets of parallel lines, and in each vertice I have a right angle. Now this is the definition of a rectangle, and what I'll have to go back to what I know. I can't just start drawing things around. So what I know is that in order to find a centroid for this rectangle, I need to relate back to what I know. So I know that if I construct two triangles and I find centroids of both, then the medium of the distance between the centroid of this triangle and into this triangle will give me the centroid of the whole figure. So I'm gonna go ahead and input that. What I have done thus far is found the midpoint of each segment in my rectangle. Next, I need to start connecting from my vertice to my opposite midpoint of the opposite segment. At this point, I have finished connecting all my midpoints to their respective vertices, and the next thing to observe is that I have found my centroids for the two triangles. And how do they connect to the centroid of the rectangle in general? Well, this is my centroid of the first triangle, and that's the centroid of the other triangle. Now they form a linear segment, and in the middle of that happens to be the centroid for the whole figure, which is a rectangle. Now it's just another thing to observe is that the diagonals of the rectangle meet at that same very point. Now,